Hello and welcome to Algebra II with Mr. Clausen. Today I am going to finish my properties of logarithm lecture that I had in my previous video by expanding on this idea of real-world applications of properties of logarithm examples. So to wrap up this topic, I want to talk about a real-world application that involves how a sound barrier along a highway reduced the intensity of the noise reaching a community by 95%. By how many decibels was the noise reduced? And a really cool thing about sound examples is that, when we're looking at these log base intensities, it's a log base 10 function. So specifically when we look at loudness, let's say we have the loudness of something. This is going to be loudness, which is going to be in units of decibels. And this is always equal to 10 times the log base 10 of your intensity over intensity naught. All right, and this intensity here is in units of watts per meter squared. And this refers to intensity. And when we think about intensity, right, you should be thinking about how hard it's beaten on your eardrum, for example, when you're experiencing it. And the number that we divided by this I naught is a constant that is deemed to be so quiet that it is not observable, all right? So there are vibrations and intensity that is around you that you may perceive as being completely silent, all right? But it still has a relative intensity. It's just something that we can't observe as humans, or maybe don't have these sensors in order to analyze. Okay, so we don't necessarily need to worry about that unless you want to just know the loudness of something, right? Then you would need to know that number. But if everything's comparative, which are the two examples that I'm going to show you here, then we can kind of get around and don't need to know that necessarily. If you do have a problem that it's just asking for loudness, I will give you I naught, or it's something that you can look up if it's needed. So when we're looking at loudness, what's really cool about the nature of logarithms is that if you reduce the noise reaching a community by a specific factor, like 95%, that can actually be measured by a specific number of decibels, right? And so what this allows us to do is, let's say we have loudness 1 here, and let's say loudness 2 is equal to the same logarithm, but we just have a new coefficient 2 here for intensity 2 and I naught. All right, and so let's say, for example, I1 is the original intensity and I2 is the reduced intensity. And what we can do is, if we want to figure out how many decibels is kind of the target, right? Because it's hard for us to measure intensity directly, but we can take a decibel reader and figure out, how many decibels we want to reduce something by. We can go and we can set up the problem by saying, hey, the original loudness minus the new loudness will give us a number of decibels that we're aiming for, and this will equal 10 log of I1 over I naught minus 10 log of I2 over I naught. Right? So from a mathematical perspective, this is how we would do it. This is really the main relationship you will need to know for any loudness or sound type problem. All right, and then if you're asking for a reduction or comparison in that way, and you're looking for the change of loudness, let's say delta L, this is always going to be the circumstance that you're going to be looking at. And it makes sound problems relatively simple because the format's going to be the same in almost every circumstance. So then the pieces that you're going to need to figure out is, how do certain pieces of information relate to each other? Well, the main piece of information that you will need to see how they relate to each other in this specific circumstance is the 95% reduction. All right, and they're saying specifically the intensity of the noise reaching the community is being reduced by 95%. So, for example, one of the ways that you can overcome some of the challenges with this and actually answer this question is say, how does I1 relate to I2? How does the original intensity relate to the reduced intensity? Well, we are really targeting that we only have 5% of the original intensity left relating to the reduced intensity, right? Because it's being dropped by 95%, so only 5% would be left. So if we said 0.05 times the original intensity, that would represent the 0.95 or 95% reduction being applied to this given circumstance. All right, so if you can find this relationship, you are well off on your way to solving this problem. All right, and even if you don't see that right away, you could still try to separate pieces out and put the pieces together using the properties of logarithms. But if you see this relationship now, go for it and plug it in, because what this will allow us to do is we can now say 10 log of the original intensity divided by the intensity naught, and 10 log I1 times 0.05 all over I naught. All right, and so I wrote it in a little bit different format here. It's the exact same thing. It's just this associative property that I'm using to be able to rearrange that a little bit. And so what I want to do in this particular circumstance is I want to find the difference of intensity. And one of the things I'm going to do here is I'm going to look at this specific portion right here, kind of factor this guy out a little bit, and I'm going to use the product property and separate these logs out. So for example, what I want to do is I want to say log I1 over I naught plus log of 0.05. So what you're going to see is I can take this part here and using that product property separate this out. I'm going to put this back in parentheses and say 10 minus 10 log of I1 over I naught. All right, and one of the reasons that this is a really useful way to break this apart is that I'm looking at this and going, oh, after I distribute this negative 10 back in to both of these components here, this will be the same as this part. All right, so for example, I'll have this and I'll say 10 log of I1 over I naught minus 10 log of I1 over I naught minus 10 log of 0.05. And I'll see that these are opposites of each other, so they will just cancel each other out. And the original part that I have up here, the L1 minus L2, will simply be equal to negative 10 log of 0.05. And since this is a number less than 1, it'll be a negative number. All right, negative 10 times the log of this number will be equal to 13.01 decibels. And so with a problem like this, and by applying knowledge of these logarithmic properties, we can actually take a loudness problem like this, and we can actually determine the number of decibels that a barrier would need to absorb or reduce the volume by in order to reduce the intensity by 95%. So if you want to reduce the intensity reaching your community by 95%, you just drop it 13.01 decibels. It doesn't matter if you're at 100 decibels or 70 decibels or 60 decibels. You reduce it by 13.01 decibels, you reduce it by 95%. If you want to reduce it by another 95%, you just keep reducing it by that increment of decibels, and you would be able to obtain that. And so I want to look at another problem now that we've talked about this little tidbit of knowledge, and look at how this would relate to earplugs, because you can look at earplugs from Menards or any other hardware store, and it'll tell you on the back like the decibel rating that they're good for. So they'll say that it reduces the volume observed by 19 decibels. So they're not telling you that it's going to, cut it by, in half of all intensity or anything like that, but they are telling you a relative decrease in intensity that your ears will observe. And again, this is relative, right? Like if you're at a concert and the volume is 120 decibels, right, that is a really loud concert. Like your ears are really going to be begging for mercy there. But if you are talking to someone and they're talking really quiet and it's maybe like 60 decibels, and you cut that by 19 decibels, they're going to be really quiet. Like you probably won't even hear them. All right. So let's look at a problem like this and figure out how we could actually solve for the amount of intensity reduction by wearing a pair of earplugs that reduces sound by 19 decibels. All right, so a nice thing about a problem like this is that, the L1 minus L2 that we were talking about previously is 19 dB, 19 decibels. And that this is going to be equal to the 10 log of I1 over I naught minus 10 log I2 over I naught. All right, and really this is all the farther we need to go at this particular point for now, because what I'm going to do is I'm going to factor out the 10 in both of these, because that's the greatest common factor between these two portions. Right, so 10 in log I1 over I naught minus log of I2 over I naught. Okay, and again, the only thing different with a particular circumstance like this is I'm trying to take advantage of the properties of logarithms. And to do that, we sometimes have to do some creative things. And between these two examples, you should be able to see a lot of the different types of variations that you might encounter. And so with something like this, I'm looking at this and going quotient property, all right? And if I can use the quotient property, what I'm going to get here is that I'm going to set this equal to 19, and then we'll have 10, and then what we'll do is we'll do log, and I'm going to go I1 all over I naught, and divide all that by I2 all over I naught. And again, a really cool thing is two things in denominators. Kachiga, they'll all cancel out. And when we go and rewrite, we'll go 19 equals 10 to the log of intensities, or the ratio of intensities. I1 being the original intensity, and I2 being the reduced intensity. All right, because that's the subtracted logarithm. And so what I'm going to do here is I'm going to divide both sides by 10. And this will give me 1.9 equals log of I1 all over I2. And remember from the pH video that when you have a log here, and it's log base 10, and let's say I just want to find the ratio, because if I find the ratio, I can find the difference in intensities. What I can do is I can take 10 to the 1.9th power and go 10th to the power of log of these ratios. And since 10 to the power of log base 10 are inverses to each other, they cancel out and equal 1. And so what we can do is, looking at the difference between L1 and L2, this is going to be equal to I1 over I2, which is going to be equal to 10 to the 1.9th power. And now we can look at an example like this. What we can do is we can plug this given value into a calculator. This is equal to 79.4. All right, and this is the ratio between I1 and I2. And if we wanted to compare that, what we're going to see is that I1 is equal to 79.4 I2. And now we can see that I1, for example, is 79.4 times more intense than I2. Or if you want to look at it like the previous example that we did, what we can do is divide both sides by 79.4 here. And all I'm going to tell you is just go 1 divided by 79.4 in your calculator. And what you will see is that this is going to be equal to 0.01, let's just say 3 I1 equals to I2. And so what this will represent is that if we go 1 minus 0.013, this will be equal to 0.987. And this would be a 98.7% reduction in intensity. And this would be a 98.7% reduction in sound intensity.